Hello everyone, welcome back to my YouTube channel. In this particular video, we'll be looking into the geometric intuition behind Perceptron. If you remember in the previous video, we have seen Perceptron in detail. We have seen each and every component starting with input nodes, the bias term, the summation term, where we calculate the weighted sum of every single input, and then the activation function node. We have seen the two phases of training and testing of Perceptron with the help of an example. We have solved that particular example step by step. And if you remember, in that particular example, in the testing phase, we understood that the Perceptron, while training itself, will finalize the weights, and that finalized weight will be used in the testing phase just to create the general expression, and whenever any new input data comes into picture, we can just fill all the values of that input data into that particular general expression, and once we compute the value, we will get to know what will be the prediction for that particular instance. Now, you might have got a question that why Perceptron changes its weights. Obviously, the Perceptron changes its weights only when it finds out a misclassified data point. And whenever any misclassified term is encountered, what makes it to change its weight, and after changing the weights, what makes the prediction to be correct. Now we will get the behind the scenes of why Perceptron changed its weights by looking at its geometric intuition. So let's start. If you remember, in the previous video we have seen that we used this particular expression to find out the weighted sum. We also have seen how this particular expression has been derived. This expression is only for two input features, that is x1 and x2. w1 and w2 are the weights associated with it. If you remember, this particular term x0, we have discussed it in the previous video. This term x0 is a virtual input, and the value of this virtual input is always set to 1 because we are interested in the weight associated with that particular virtual input. So let's replace x0 with 1. Now you can see that anything multiplied by 1 is that particular term itself. So 1 into w0 is w0. Now you can see this particular expression w0 plus x1 into w1 plus x2 into w2. Let's take this w0 at the end instead of writing it at the first. We haven't changed the value of this expression, we just have shifted first term to the last, that's it. Now here if you observe, we have the terms to be x1 into w1 and x2 into w2. So instead of writing x1 into w1, can I just write it w1 into x1? The meaning remains the same, we just have written the weights first and then we have written the variables. Once again I'll tell, we haven't changed the value of the entire expression, the value remains the same, we just have shifted some terms. Now once we got this expression, let's replace w1 weight with a, w2 weight with b and w0 weight with c, and also we will replace x1 variable with x and x2 variable with y. Here we are just changing the representations. Once you replace all the terms, you can see the expressions boils down to this particular expression, ax plus by plus c. Now just try to strain your brain and try to recall where you have seen this expression. Doesn't that look like the equation of a line when we equate it with 0? Yes, it is the equation of a line. We have equated this particular expression with 0 because in the previous video we have seen if the value of this expression is lesser than 0, then the data point lies in class 1, and if the value of this expression is greater than or equal to 0, then it lies in class 2. Now let's try to visualize this particular equation of a line with an example. Let's first write the generalized equation of a line. You can see it is ax plus by plus c equal to 0, where a, b and c are the weights here and x and y are the variables. Variables means the feature input. So let's try to change the values of a, b and c, and let's see how the line gets plotted. So here let's set the value of a as 4. So you can see a becomes 4, and let's set the value of b as 8 and c as 1. So you can see our line is plotted. And now I hope you understand why weights play an important role in Perceptron. Now if we change the value of a, that is the coefficient of x variable, you can see it rotates on y-axis, and if we change the value of b, that is the coefficient of y, it rotates on x-axis. And if we change the bias term weight, that is the value of c, then you can see how it shifts itself with respect to the axis. Now I hope you understood the significance of each and every term in this particular equation of a line in terms of geometry. If you remember, in the previous video we have taken this particular example, we'll take the same example in this particular video also. Here temperature and humidity are the features and climate is the label which we have to predict. Now you can see here we have two features. Now if we want to visualize this, we can write it in terms of coordinates. First record contains the temperature 32 and humidity 80. So it becomes the first coordinate, that is 32, 80, where 32 is the x value and 80 becomes the y value. Similarly, we can do it for the other records also. So here we get the 4 coordinates. Now let's try to again come to this particular tool and let's visualize this. So here I have written the 4 coordinates. You can see first coordinate 32, 80 comes out to be like this on the 2D graph. Similarly, you can see the next coordinate, that is 25, 60. The point comes here. Similarly, the third coordinate, which is 28, 75, you can see it here, and the fourth coordinate, which is 20, 50, you can see it over here. So this is the orientation if we visualize the records from the dataset. Now, if you remember, in the dataset we had labels also. So let's write the labels for this particular records also. Here you can see for the first record the label was tropical. For the second record the label was balanced because the data point was from the balanced class. The third record was from the tropical class and the fourth record was from the balanced class again. If you look carefully at the orientation of this particular coordinates, you can see all the tropical points are on one side and all the balanced points are on one side. Till here I hope everything must be clear. Now let's move on to some other things also and let's come back to this tool again. So this was the expression that we finally got after shifting some of the terms. Now in this particular expression, if you remember initially while training the previous example, we had set all the weights of all the features to 1 because initially we have to set it to 1. We don't know which feature is more important than the other. That is why we give it the same value. The value can be any random value, but every weight must be same. Now this was for the initial stage when we were about to start training. But after training, if you remember in the previous video, we have got the final weights to be this. The coefficient of the x1 variable was 2, the coefficient of x2 variable was 3 and the bias weight was minus 250. This particular expression we got. And for any new unseen data, we used this expression for prediction. Now why we used this particular expression and not the initial one? What makes this expression correct so that it can be used for prediction purpose? Let's visualize it and we will come to know the insights of this particular expression. So we have already seen the orientation of this particular coordinates. Now let's introduce those expressions before training as well as the expression that we got after training. So initially the value of all the weights were set to 1. That was the value of A, B and C. So here in this particular expression, we'll write the expression as 1x plus 1y plus 1 equals 0. And here you can see the line is something like this. You can see this line divides the entire region into two parts, the left one and the right one. Now one question comes, how we can get the access to these two particular regions? The answer is simple. If we write the expression to be greater than 0, then we get the right hand side region, which you can also call the above region. Similarly, if we want to get the access to the left region, that is the below region, we can write the expression to be less than 0. You can see we have got the access to these two particular regions. Now why we want to get the access to these particular regions? Because if you remember the data set, there we had two classes, one is the tropical and one is the balanced. Somehow if we try to make all the tropicals to the above region and all the balanced data points to the below region, then we can easily separate these two particular classes and we will be able to now make the predictions. But do you think this particular line is able to separate the two classes, tropical and balanced? No, right? This particular line has all the data points onto a single region. So we will have to somehow manipulate the expression in such a way that this particular line will be able to separate the two classes, one for tropical and one for balanced. So we can change the orientation of this particular line by altering the values, that is the weights of the expression. Now here, the concept of how we change the weights totally depends on the mathematical intuition behind perceptron, and the mathematical intuition is nothing but the algorithm what it uses to change the weights. We'll look at it in the next video. Now if you remember, this was the expression, that is 2x plus 3y minus 250 equals to 0. This expression we got after proper training. And you can see this particular equation is actually able to separate the two classes, that is the tropical ones on one side, that is the above side, and the second, that is the balanced one, on the below. So for any input features, if the value that we obtain after substituting it in this particular expression, that is 2x plus 3y minus 250, if we get it greater than 0, then the data point will lie on the tropical region, and if it is lesser than 0, then the data point will lie in the balanced region. Here you can see in the general expression, the weight W1 value is 2, the weight W2 value is 3, and the bias term weight value is minus 250. Here you can see W2 is greater than W1, that means the humidity feature is more important than the temperature feature for this particular data set. So I hope the geometric intuition of perceptron for two input features is clear to you all. Now that was for two input features. What if we have more than two input features? Let's say in this particular data set, with temperature and humidity we get one more feature, that is wind speed. Then in this particular case, what exactly the scenario will be? Let's have a look at it. So you can see here we have three features and one label. Here again we have two classes only, that is the tropical and the balanced one. We just have added one feature. Now if we add one more feature, we will get three values to represent a coordinate, that is x1, x2 and x3. Here now the expression will also become w1 into x1 plus w2 into x2, and since x3 is introduced, so weight associated with it will also be introduced, that is w3. So therefore one more term will be added, that is w3 into x3, and we readily have the w0, that is the bias term weight, and this entire expression when equated to 0 will now represent the equation that will be used for separating the two classes. Now if you substitute the weights w1, w2, w3, w0 with a, b, c and d respectively, you will get this expression ax plus by plus cz plus d equals to 0. And if you strain your brain again, you will come to know that this equation is nothing but an equation of a plane. You can see that once the features are added, this expression is also getting more terms. If you carefully observe, for two features we had a 2D graph to represent these things. For three features we will now require 3D graph for representing the geometric intuition behind this particular scenario. So just remember n dimensions for n features, and let's visualize this thing now. Here I have plotted all the four data points and the orientation looks something like this. Here I also have written the labels with respect to this particular data points. The first one is tropical, the second one is balanced, the third one is tropical again, and the fourth one is balanced. Now after plotting these records, you can see that the points that are associated in class of tropicals are on one side and the points in the class of balanced are on the other side. Now we need something that will separate these two classes in two regions, and for that we will use the equation of a plane which we have seen, that is ax plus by plus cz plus d equals to 0. By changing the weights a, b, c and d, we will get the plane. Initially before training we don't know which feature is more important, that is why we initialize the value to be same for all the weights. Here let's initialize the weights to be 1 and you can see that the plane looks something like this. Now this particular plane is not responsible for separating the two classes, tropical and balanced. That is why we need to change the weights in such a manner that this plane will come in between the two classes and will be clearly able to separate the two classes from each other. So that we'll get the two classes data points in two separate regions. And let me tell you again, there is a mathematical intuition behind changing the weights so that we will get the exact separation for these two particular classes. This training rule and the mathematical intuition, we will look into it in the next video. Now you can see here, after manipulating the values in the equation, final equation that we have got is 20x plus 30y minus 2z minus 2500 equals to 0. With this equation, we got this particular plane which is clearly separating the two classes, that is the balanced and the tropicals. If any new unseen data arises, we can use this particular expression and we just have to put the values in place of x, y and z. And once we put it, if we get the value lesser than 0, then it will lie in the balanced class region, and if it is greater than or equal to 0, then it will lie in the tropical class region. So I hope the 3D intuition for this 3 feature dataset is clear to you all. Similarly, if it is 4 features, then we will require 4 dimensions and so on. So I hope everything related to perceptron geometric intuition is clear till now. Now, what if we have the orientation of data points something like this? Now in this particular case, you can clearly see that there are two classes. One is the class of red circles and another is the class of white circles. But you can see we cannot separate these two classes with a line. Wherever you draw a line, you won't be able to separate completely these two classes. And in the real world scenario also, we get this particular data. We do not get a data where we can completely separate the two classes with just a single line. You can see I have drawn this particular line and still we are not able to separate the two classes, red and white. Similarly, if I try to draw another line, then also I will not be able to separate this. So from this, what you can observe that this perceptron rule will not be applicable when the data points are not linearly separable. In the previous case, we were able to clearly see that all the balanced data points were on the one side and all the tropical data points were on the other side. But here the case is not like that. That is why here we cannot deal with this particular data with the help of perceptron. And this is the drawback of perceptron, that it does not work on non-linearly separable data. So now I hope the entire geometric intuition behind perceptron is crystal clear to you all. I have tried a lot to visualize each and every aspect and I hope you have got the insights of it. Now let's try to visualize everything that we have seen till now with the help of code. Here I am going to use the inbuilt perceptron from sklearn. So first, let's import all the important libraries that we are going to use. NumPy, Pandas, Plotly, Plotly Express, Plotly Graph Objects. I'll be using this for visualization purpose. Let's import all these libraries, and now here I have taken the same dataset that we have seen in the previous example. Here the dataset is of the climate, and let me first show you the data file. Here it is a text file and it contains 94 records. Here you can see temperature and humidity are the feature columns, and the label column contains two classes, that is, one is tropical and second is balanced. So here we have total 94 records and in all we have 3 columns. We'll use this dataset and we'll store it in the variable df. So let's execute this particular cell. You can see over here this particular cell consists of 94 rows and 3 columns, and you can see this is the table. Let's close the text file for now. If you carefully observe the label column, which contains the two classes tropical and balanced, these are text values. Here we don't want the text values, so we will be using the label encoder to convert these values into numerical values. For tropical class, we'll assign the value 1 and for the balanced class we'll assign the value 0. Let's execute this particular cell, and after executing it, just for checking whether it has changed the things, we will again see the dataset. So here we'll execute the df variable, and you can clearly see that the tropical ones are now converted into 1 and the balanced ones are now converted into zeros. So that is why we have used label encoder. Now once we do this, now let's try to visualize the orientation of these two features with respect to the two classes, that is the tropical ones and the balanced one. Here on the x we are plotting temperature, on the y we are plotting humidity. With respect to the label, here we are going to use different colors for both the classes. So you can see here the scatter plot has been plotted, and you can see the yellow ones are nothing but the tropical class data points and the blue ones are nothing but the balanced class data points. You can see both these classes are linearly separable. That means we can use a single line to separate these two classes from each other so that it can be in different regions. So this is the orientation of the two different classes. Now from the dataset, let's separate the features into x variable and the label column in y variable. So here with the help of iloc, we are just storing the first two columns, that is the columns that are present on index 0 and 1, into the variable x because they are features, and the column that is present on index 2, which is nothing but the label column, will store it in the variable y. So we have separated the features and labels. Now, as I already told you that we are going to use inbuilt perceptron, so I have written from sklearn.linear model import perceptron, and let's store this perceptron in the variable perceptron. So let's try to fit both the features and label in the perceptron. So here you can see we have executed it, and with this the perceptron is now trained. Now you know that a perceptron contains weights as well as bias weight. So here with the help of this .coef underscore, that is the coefficient, we can get all the weights of all the input features, that is for temperature as well as for humidity. You can see we get an array, and first value is for the weight that is associated with the temperature feature, and the second value in this particular array is nothing but the weight that is associated with the humidity feature. So after proper training, we have got this particular weights, and similarly we also have a bias weight. We represent it with the help of the variable intercept underscore. So when you execute this, you will get the bias weight, and here we have got this bias weight after training for our features. Now once we have got this, we can now visualize the decision boundary that is created just to separate these two classes, that is the tropical ones and the balanced ones. So for visualization, I am going to use Plotly. Here I have written some piece of code, and don't worry about this particular code. Even if you don't understand it, it's okay. We'll go into it step by step in upcoming videos. But for now, just understand that this particular code will be responsible for plotting the decision boundary between the two classes. Let's execute the code, and here you can see we have got this particular decision boundary, and you can see now all the tropical ones are in one region and all the balanced ones are in the another region. This decision boundary we have got with the help of Perceptron because it has given us the finalized weights as well as the bias weight, through which we have got the general expression. And now with this general expression, whenever any new unseen data comes, we can easily classify it. You can see the decision boundary is plotted in such a manner that there are no misclassification terms, but in real world cases it might not be like this. But for now, just for understanding purpose, I have used this simple data just to show you how we can visualize the perceptron and its output. So I hope you have understood each and every single insight that we have seen in this particular video with respect to perceptron. If you guys get any doubt, post it in the comment section, post your reviews and suggestions also. Share it with your friends, and for more such videos, do like, share and subscribe. Also hit the bell icon and don't forget to follow me on Instagram. Thank you so much for watching. Have a good day ahead.